Example 4. Find a formula for a cubic polynomial, ax cubed plus bx squared plus cx plus d, that has a critical point at x equals 4 and an inflection point at 2, 5 and a leading coefficient of 1. So if we have a leading coefficient of 1, that means that a equals 1. If we're talking about a critical point, we're talking about where the first derivative equals 0. And if we have an inflection point, then we're talking about the place on the original function where we change concavity. So we'll come back to that in a minute. So the function that we're looking for, we need to find a, b, c, and d. We already know a. A is 1. So now we have x cubed plus bx squared plus cx plus d. Let's find the first derivative and see how we can use our information about the critical point to see if we can get any further information about these b, c, and d constants. So my first derivative here is 3x squared plus 2bx plus c. Now, if I have a critical point at x equals 4, that means that if I had set this equal to 0 and solved for x, one of the values would have been 4. That also means that if I plug a 4 into my first derivative, then the whole thing will have to equal 0. So here, if I plug in a 4 everywhere, this is going to have to equal 0. So this is 48 plus 8b plus c equals 0. Unfortunately, I'm not able to solve for either of these constants yet because I have two constants and one equation. So I want to keep working and see what else I know. Maybe this equation will become useful to me in a little bit. So I also know something about the second derivative. So let's go ahead and compute the second derivative, and then we'll talk about that. So here, the second derivative, I'm going to go back to the unfactored, uncomputed form of the first derivative, and I'm going to get 6x plus 2b. Now, I want to talk about this inflection point. The inflection point on the original function is at the point 2, 5. When we've talked about inflection points and we've solved for things using the second derivative in the previous problems, we always did it in terms of where the x was. So we're talking about where things happen in terms of the independent variable. That 0.25, the whole point, only applies to the original function. However, the 2, the independent value, tells us where something happens. So if we have an inflection point, then that means that at 2, our second derivative should equal 0. Because to the left of 2 and to the right of 2, we should have different signs of the second derivative. And in order for it to change signs, it has to go through 0. So again, the 5 is not relevant to the second derivative, but the 2 is. So here, if I plug in a 2, I get 12 plus 2b, and that will have to equal 0. Because again, to the left of 2 and to the right of 2, we should have different signs, which means that at 2, we had to go through 0. So now I can solve for b. So if I subtract 2b to the right, and then I divide by the negative 2, I get b equals negative 6. So that's great. Now I have my second number here. The first one was a equals 1, but now I know that b equals negative 6. Well, let's go back to my first derivative function. I was stuck because I had two unknowns, but now I know one of those unknowns, and so I can substitute that in. So if I substitute in that b equals negative 6, I get 48 plus negative 48 plus c equals 0. Well, that means I have c equals 0. So now I have another one of my unknowns. So far, if I go back to my original equation, I know a, b, and c. So let's rewrite our original equation with what we know. So now we have f of x equals 1x cubed minus 6x squared plus 0x plus d. So now I want to go back to this inflection point. So the inflection point tells me where exactly on the graph my function is changing from concave up to concave down. However, it also tells me the relationship between x and y for this function. It's a point on the original function. So that means if I were to plug a 2 into f of x, that the whole thing would have to equal 5 as my y value. So 2 cubed is 8, minus 6 times 2 squared is 24, plus d has to equal 5. So 8 minus 24 is going to give me negative 16. I'm going to add that over to the other side, and so I get 16 plus 5. So that tells me that d has to equal 21. So now I have my a, my b, my c, and my d. So I'm able to write my final answer here, which is x cubed minus 6x squared plus 21. So this is the cubic equation that satisfies that we have a critical point at 4 and an inflection point at 2, 5 with a leading coefficient of 1. So we're able to use what we knew about the first and second derivative to match up our information and solve for our unknowns. Let's look at another. Example 5. Suppose we have the following information regarding the first and second derivative of a function. So here we have some derivative maps. The top part here is telling you what's happening at the first derivative. It's telling you the sign and where the first derivative equals 0. So here, if we're considering where the critical points are, we have to consider both where the first derivative equals 0 and if there's any places where the first derivative is undefined. So the first derivative is the first line on the top here. So my first derivative is going to equal 0 at 2 and at 0. So I'm going to have critical points at x equals 2 and x equals 0. Because again, that's where my first derivative equals 0. Now, if I wanted to find out what kind of critical points these are, I could use my first derivative test here to figure out if these were local maximums or local minimums or neither. So I want you to notice what's happening at 0. To the left of 0, we have that my first derivative is positive, and to the right, I have again that my first derivative is positive. So here, my first derivative didn't change signs. So x equals 0 is not a local max or a local min. However, if you look at 2, to the left of 2, my first derivative is positive, but to the right of 2, my first derivative is negative. So if your first derivative changes from positive to negative, that means your original function was increasing and then decreasing, which means 2 is a local max. So that's some interesting information to figure out here. For part B, we want to figure out for what x values that we have inflection points. So we can see that our interval is divided up at 0 and 1. So to the left of 0, my second derivative is negative. To the right of 0, my second derivative is positive. So that means that at 0, I'm going to have an inflection point because the concavity changed. It changed from negative to positive. So that means it was concave down to the left and it was concave up to the right of 0. So x equals 0 is an inflection point. And then the other point that I have to consider is what's happening at 1. So that's another place where the second derivative equaled 0. To the left of 1, we're positive, so we're concave up. And then to the right of 1, we're going to be negative, so we're concave down. So again, we change signs around x equals 1. So x equals 1 is also an inflection point. So we found here that we have two inflection points, one at x equals 0 and one at x equals 1. I also want to point out that once we had determined that we had a critical point at 2, We could have used the second derivative test to find that it was a local max, because if you notice here that at 2, we have that the second derivative is negative, which means it's concave down, which would have also told us that it was a max. We use the first derivative test, but all your tests should give you the same answer if they're not inconclusive. So that's how we read these types of maps in terms of what sign the first and second derivative are and where these things equal 0. Let's do a couple of examples where we have information about the first derivative and we want to use that to talk about inflection points. Example 6. Suppose the derivative is given in the graph below. I want to use that graph to determine the inflection points of the original function on the given interval. So remember, if you have the derivative, we're interested in where we have horizontal tangent lines because they're going to help us find the places where our first derivative changes from increasing to decreasing or decreasing to increasing. So what I want you to notice here is that this is increasing, which tells me that the second derivative is positive on this little interval. So that looks like it's about negative 1.5. And then my first derivative is decreasing from negative 1.5 to positive 1.5, which tells me that my second derivative is negative. So I can see that at negative 1.5, I've changed from positive to negative. So that's my first inflection point. Now here from 1.5 until about 4.75, this function is increasing. If your first derivative is increasing, your second derivative is going to be positive. So again, I can see that here at 1.5, to the left, my second derivative was negative. To the right, it was positive. So positive 1.5 will be an inflection point. Here at 4.75, to the left, we were increasing, so my second derivative is positive. To the right, my first derivative is decreasing, so my second derivative is negative, and therefore I again change signs on the second derivative. So 4.75 approximately is also an inflection point. So here there were 3 places where I changed from increasing to decreasing or decreasing to increasing, which means the sign of the second derivative changed. And if the sign of the second derivative changes, that means the concavity of the original function changes, which means we have an inflection point. So there were 3 places I was able to identify where I have an inflection point on the original function using the first derivative graph. Let's look at another example. Example 7. Suppose that f of x is a continuous function that is differentiable. Given the table of the values for the derivative f prime of x, determine the most likely places that f of x would have inflection points. So again, when we have information about the first derivative, we're looking for the places where we change from increasing to decreasing or decreasing to increasing, because that is where the second derivative is changing signs. So let's look at the values of the derivative to see what we can figure out. Negative 14, negative 8, negative 4, 0, 5. That set of numbers is increasing. They're going upward when you think about a number line. So they're becoming less and less negative at first, then they go to 0, and then they become positive. 5, 2, negative 1. So those numbers are decreasing. So they're going down as you look at the values. So that tells me that right around x equals 8 is where I'm changing from increasing to decreasing, which means that right around x equals 8 is where I would have a horizontal tangent line and is where my second derivative would be changing signs from positive to negative. It's going to be positive at first because the derivative was increasing, and then it would be negative afterwards because it was decreasing. So that tells me that I'm most likely to have an inflection point around x equals 8. Now again, it's not precise. It might happen at 7, it might happen at 9, but based on the data we have from this table, that's our best guess. And so again, our inflection point is going to happen right around 8. So because our second derivative will be positive to the left of 8, that means on the original function, we will be concave up. Because we're going to be negative to the right of 8 in the second derivative, that tells me that the original function will be concave down. So for this inflection point, we're changing from concave up to concave down around x equals 8.